Hello, this is the 10th video for this series. So today we will discuss the operators and then in relation to eigenvectors and the upper triangular matrices. Yeah, last time we introduced the notion of invariant subspace, specifically um, invariant subspace with respect to linear transformation or linear map T. So sometimes people put T invariant here with respect to the specific linear map T. Then we have eigenvalues and eigenvectors. Now we will start with polynomials uh, applied to operators. So basically, operators, recall that operator is just a linear map. E is just a linear map from our vector space itself, and then with this here is just, we denote this as LV, okay? And then the resurry here comes from, because this is just a vector map, linear map from vector space itself, we can raise the linear map into powers. Okay, and then we can think of this as a concept of the key concept of applying a polynomial to an operator. So let me define that properly. Starting with number 1. So we define here suppose T is a linear map or a linear operator, an operator, and here M is a positive integer. Then we define T to the M, the powers of T is just equal to T here, then multiply it T times, M times, and then we will define T to the 0 with the identity on the vector space V. Okay, and of course, we have T raised to -1 is, me phrase it nicely. If our T is invertible, denote T -1 as the inverse of our linear operator T, and then define your, okay, wrong spelling. Define your T raised to -M it's just equal to T raised to -1 or the inverse of T, M times. So these are some facts that are left for verification, but the usual exponentiation is true. And then we have T raised to M and raised to N, it's just T raised to M times N. Here, M can be any integer if our T is invertible. Now let us recall the definition of the of a polynomial that I skipped. Polynomial is just the usual polynomial that we have in high school. So here T is a linear operator on V, and here T is a polynomial in the with coefficients in F. We denote P of Z. This is Z is our indeterminate, so A0, A1Z, and then up to A, M, Z to the M, where here our Z is the an element of F. Now, the operator, your P, respect to the linear map T, is the operator P of T given by A0 I plus A1 T plus A2 T squared, and then up to A M T to the M. Okay. Let us consider an example. This D here, a linear operator on the polynomial with coefficients in R, and then D is defined as follows. D of the Q is Q prime, and our P is given by 7 minus 3x plus 5x squared. Then your P of D is just 7, the identity, minus 3, okay, minus 3 times the operator D plus 5 times the operator D squared. Thus, if we get P D of Q here, this is just 7Q minus 3Q prime plus 5Q double prime. Because here, D is just the derivative linear operator, then this is for all Q in the polynomial ring with coefficients in R. So, okay. So, remark, if fix yung operator T in the linear, as a linear operator, then the function from the polynomial ring to the set of linear operators given by P map to P of T. This is a linear map. It's a linear operator. Linear is linear. Is a linear function. So we define the usual notion of products. If P and Q are polynomial with coefficients in R, then your P Q of Z is just equal to P of Z, Q of Z, for all Z here in the field F. And we have some theorem or proposition here. A PQ of operator T is equal to P of T, Q of T, and then P of T, Q of T. This is equal to Q of T, is P of T. The proof here is just easy verification. Now we go to the relationship between operators and the existence of eigenvalues. So let me underline this and then state a theorem. So here's the theorem. Every operator on a finite dimensional vector space, finite dimensional, say non-zero vector space over the complex numbers has an eigenvalue. So let us prove this statement. Your assumption is B is a complex, let B be a complex vector space. Of course, non-zero, and then finite dimensional. And then here, let dim V be equal to our N, which is, of course, greater than 0. And consider arbitrary operator T. And now, choose a vector non-zero, here a vector in V. Then look at the operator applied to V. So here we have T of V, and then T squared of V, and then T to the N of V. Okay. This set, there are how many? N plus 1 of these. Because there are N plus 1 of these, they are not linearly independent. Since the dimension, the independent with respect to V, since the dimension of our V is equal to N, and there are more, they are more than N. Thus, we can express 0. Thus, we have 0 is equal to A0 V plus A1 T of V up to AN T of V, T raised to N of V. And then A1 A sub i's not all 0 because of the not linearly independent. And so here, we make the coefficients of the polynomial, you factor this factor. So here, let us consider our A, the coefficient of the polynomial. Of our polynomial. Here, star. And then we make a polynomial out of this. So this is A0 plus A1Z plus up to AN Z to the N. So this is over the complex numbers. So by FTC, fundamental theorem of not calculus but algebra, your P here can be written as constant Z minus lambda 1, Z minus lambda 2, and then up to Z minus lambda M. And here we have C is a what? C is non-zero complex number. Oh, wait. C is non-zero, and then C is an element of not Z, but an element of the complex number. And then each lambda sub j is also in C. Why can we do this? Why can we do this? Because of the fundamental theorem of algebra, it states that every polynomial with coefficient in C as factor, it can be factored. So here, note that M can be not equal to not equal to N necessarily, because some of them may have of AN may be equal to 0. Now we write 0 as A1V plus A1TV, and then AN e to the N of V. And here we write A1I plus A1T plus AN T to the N. And then we can factor out your V because it's just linear map. And of course, using this factorization above, you can write T minus lambda 1I, and then T minus lambda 2I up to T minus lambda MI, which means that our T minus lambda JI is not injective for at least one of the J's. If this is not injective for at least one of the J, then your T has an eigenvector, an eigenvalue. And of course, if we have an eigenvalue, we can always compute for eigenvectors. So there are other ways to prove this statement. This is outlined in exercise 16 and 17, but a slightly different method or technique. Now we will define, we'll go to the section on upper triangular matrices. So these are introduced previously. So let me define this formally today, in this video. So here we have a linear operator on V, and we get a basis of our vector space V. Then the matrix of our operator T with respect to V1 to Vn is the n by n matrix M of T, which is just here A11, and then here A1n, here ANN, and here we have A1n. So yeah, diagonals. Here A, J, K are defined by your your map T of V sub K. V sub K is just A1 K times V1, and then plus A N and K times Vn. Okay. So you can think of this as the operator applied to our vector V, and then this is just the same from the development before, but here we just fix our M and N to be equal. if uh, if your vector, your basis is not clear from the context, we write matrix T, and then we write the vector v1 to vn for our matrix of T here. Here is the vector specified. So here the kth column here, for example, the kth column here, A1K, and then you have A K N. No, A and K is given by the linear combinations of V1 to Vn here. If we are not given the basis, we will default basis. If not given, we use the standard basis. Let us look at an example. Here we get a T here, a linear map on F3. And then we define the T as follows. This is just 2y, oh wait, 2x plus y, and then 5y plus 3z, and then 8z. So here the matrix of the map T is given by 2, 1, 0, 0, 5, 3, and 0, 0, 8. So this corresponds here and here, and this one you get, on this part z is 0, and this part z is 3, 5, your y, and x is 0, and the rest is just repetitive process. So here the goal of linear algebra is to show that a given, one of the central goals of linear algebra is to show that given an operator, there exists a basis of V, the vector space, with respect to which T has a simple matrix. So to make this vague formulation a bit more precise, you might try to choose a basis of our vector space B such that many of the entries of the matrix will be 0. So in this, if B is finite dimensional and this is a complex vector space, and then we know that there's a basis with respect to the matrix to which the matrix of the map or the linear operator T has 0 everywhere in the first column, except possibly at the first entry. In other words, there's a basis V with respect to which the matrix T looks like the classical matrix. So now we will define a diagonal matrix and then state some results regarding what I have mentioned earlier. So a diagonal matrix, I'll just write the form. We get, this is a square matrix. And then of the entries along the line from the upper left corner to the bottom. So you just have A, B, C, D, and so on here. So the sequence Z, and all the entries are 0. And then another definition is the upper triangular matrix. So we get the diagonal lambda 1 up to say lambda sub n. Here, this is here, all entries below the diagonal are 0. So that's it. Now we get a statement on the condition on the for the upper triangular matrix and its relationship with the linear operator. So get a linear operator T, and then you fix a basis of vector space V. This is basis. Let me write this. Okay, it's supposed to be erased. This list is a basis of our vector space V. And then we have the following equivalents. Number 1, M of T is upper triangular with respect to V1 up to Vn. And then letter B, T of V sub j is in the span of V1 to V sub j here for each j from 1 to n. And letter C, we get the span of V sub 1 up to V sub j is invariant under the linear operator T for each j from 1 to n. We will state the proof of this theorem. A implies B. It's just definition. Okay. If you have a matrix with upper triangular, then you get the map of the operator with respect to V's applied to V sub 1 is in the span of this. So this is easy. And yeah, I can think about it. And here also, C going to be is true, because if the span is invariant under T, then of course T of V for each B is also inside. So this is easy, and then by definition, this one is easy because this also by definition. And we get A, B, we get C implies B. So let us draw this. A implies B, and then we have C implies B. And then what's missing? B implies C. Here, this is true. So we need to show that B implies C. Okay, let's show B implies C. Suppose B holds. So if B holds, suppose B, okay, fix our integer j, which is an element of 1 up to n. And then from V, get T of V1 is in the span of V1. Of course, it's in the span of itself, the vector containing itself. This is also included in the span of V1 to Vk, and then T of V2 is also in the span of V1, V2, included in the span of V1 up to Vj. Here I'll write instead of J also. And this continues up to T of Vj, which is in the span of V1 up to V sub j. In this case, there's no more inclusion because we already exhausted the V sub j's. Thus, your V is a linear combination of V1 up to V sub j. Why? If V is a linear combination of V1 up to V sub j, of course, then the operator T applied to V will be inside the span of V1 to V sub j. That means this means that span of our V1 to V sub j is T invariant, which is what we need to show. So that is T of V sub j is also in the span of V1 to V sub j for all j from 1 to n. So this completes the proof of this statement. Now, again, it's nice to work in complex vector space. And then more of this will be discussed in the later part of the course, which is operators and complex vector space. I think that's the what chapter? Let me see. Chapter 8. I mean, of the book. Operators and complex vector space. All right, let's consider another theorem. I have a theorem on the book. I will explain the first proof. The second proof I will leave to you for exercise reading. So not only exercise on doing problems, but here reading proofs is also a form of exercise. Let me state the theorem. V finite dimensional, then vector space, C vector space, and then we get a linear operator T. Then here, the result or the consequence is T has an upper triangular matrix with respect to some basis V. All right. So the proof here, I will use the first proof on the book and then explain this. So the technique is by induction on the dimension of your vector space V. All right. So this is clear when our dimension of V is equal to 1. So it's just it's just a matrix with like 1 by 1. It's just a number. Now we have our induction hypothesis. Suppose that the dimension of V is greater than 1, and then the hypothesis holds. This the result, the desired result holds. Okay. And then the third result holds uh, for those with dimension less than dimension of the vector space V. Okay, so this is like an inductive hypothesis. So let us consider eigenvalue. So this is guaranteed because of our previous statement that um, if you get every operator as an eigenvalue, this is proven earlier by using the fundamental theorem of algebra. So always we can assume there's an eigenvalue. So let us call the eigenvalue T. Okay, the eigenvalue here is T. Lambda, I mean, lambda, the eigenvalue. So define the subspace U to be the range of our T minus lambda sub I. Okay. This is not surjective. Here T minus lambda sub I is not surjective because lambda, it has an eigenvalue by the previous theorem. Therefore, the dimension of our U is less than the dimension of our V. And furthermore, U is invariant under T. Okay. So how do you show that U is invariant under T? Let us prove quickly this underlined claim. Suppose our U is an element of U here. Then T of our U is just T of P of U is um, this one, and then minus lambda I U plus lambda U. Wait. This is we know that this one and this one is an element of U because U is just the range of of T minus lambda I. And this one is also in U because it's invariant under T. Because this is just scalar multiple of U. And then what this implies is this implies that T of U is this is in U, this is in U, this is also in U. Hence, our U is invariant under T. So we have proven this. The key result here is we just write T of U as T, and then this is just like T minus lambda I, T of U, lambda I of U plus lambda I of U. This is like going to zero, thing like that. So we have proven this result here. And now, because this is the T is invariant in U, we can say that T restricted to U is an operator. So we just restrict the domain. So because of our induction hypothesis, by hypothesis of induction, what's the hypothesis of induction? We have an upper triangular matrix, so we get if we get an upper triangular matrix, we will use the previous result. That is, if we get an upper triangular matrix, we can have what? We can have we can have a basis of U. We have basis of our U. So your basis is U1 to UM with respect to our to which our T restricted to U as an upper triangular matrix. So this is a result of, let me go back to this theorem. Here, with respect to a basis, we just invoke that, and then we have a upper triangular matrix of our restriction, or our operator T restricted to the subspace U, and then applying the theorem for each J. For each J, T U sub J is just T restricted to U, and then U sub J. This is in the span of U1 to UJ for each J. So now you can extend your U1, UM, V1 to Vn, basis of our vector space V. And then for each K in the set 1 to K, 1 to N, we get the linear operator applied to V sub K. This is just T of lambda identity V sub K plus lambda V sub K, which is this is the same from before. So this one here is inside U, okay, which is just, this means this is just span of U1 to UM, because this one is our basis for U. This means and what? This means that our T V sub K is in the span. This one is in the span of U, and then this is in the span of V sub 1 to V sub K. This is in the span of the entire collection, U1 up to UM, and then V1 up to Vn. And because of this, we will use the equivalent statement that we have proven here. It's in the span, this one, T of V sub J is in the span of V1 to V sub J. This is equivalent to saying that our operator T has an upper triangular matrix with respect to the basis. So in this case, our basis is the U sub 1 to U sub M, and then we adjoin V sub 1 to V sub N, and then I think that completes the proof here. And then by previous theorem, the desired result follows by induction. So end of proof. Okay. So it's quite long, but there's another proof here, but I will not be. You determine how compare the two proofs, one in the book and the one here I presented. So we now consider another theorem that relates the invertibility and the upper triangular matrix. Okay, this is a quite long proof, but I am determined to write this out here. Suppose we get a linear operator T with upper triangular matrix. We will denote that with M of T with respect to basis, some basis. Then our T is invertible. This is if and only if all the entries of on the diagonal of the upper triangular matrix is not non-zero. Okay, we will prove this. This is like long. So we assume the existence of the basis B1 to Bn, basis of our V with respect to T as a matrix given by lambda 1 up to lambda n. And then we have here the non-zero part and down the zero part. Okay. We need to prove that T is invertible if and only if. Here, want to show T invertible if and only if our lambda sub j not equal to 0 for all j. And then we will show both directions. So first is b sub j not 0 for all j. Suppose this is the okay. Let me write this. This one here, and then this is the direction. Suppose that this is not 0 for all j. So this one, this of 1, up to this of n. These are not all 0. And then we get the T of V1 is just lambda 1 V1. So from our matrix M of T. And because lambda 1 not 0, we get T of V1 over lambda 1 is just equal to V1. And this means that thus your V, not V1, not Vi, but V1 is in the span of, not span, but in the range of T. All right. Now look at T2 applied to our second vector component, second component of the vector space bases. So V sub 2. We can do the same. This is over lambda sub 2 because lambda sub 2 is not 0. This is just a V1 plus V2. And then here, for some A in the scalar field. In this case, we get our what? Our V2 is also in the range of T. The left-hand side of the equation, and the AV1 are both in the range. Therefore, this is in the range. This is in the range. Therefore, V2 here is also in the range. Okay. Now, for the similar, this is similar for T of V3 over lambda 3. You write that as B1 V1 plus C2 V2 plus say V3. And then this is in the range of T. As above, this is also in the range of T, and also this is in the range of T. This means V sub 3 is also in the range of our linear operator T. So we can continue this process until we have exhausted our V sub n's. And then this means that V sub 1 up to V sub n are all in the range of our range of T. And this implies, thus, your range of T is equal to the vector space V. That means, this means that your T is surjective. And then, if we have the same dimension, surjective implies invertible. And hence, T is invertible. Okay, now we go to the other direction. Suppose that T is invertible, then we show that our lambda sub j is non-zero for all j. But here we will use proof by contradiction. And now, let us consider our j between 1 to n. For lambda sub 1, it should be not equal to 0 because it will give us T of V sub 1 is equal to 0, which is not the case. So we have already dealt with lambda sub 1. Lambda sub 1. So we exclude that. And then suppose that 1 of lambda sub j is 0, okay, for the sake of contradiction. Here, this means that the span of V1 to V sub j is there's a mapping that maps this one into your span of V sub 1 up to V sub j minus 1, which means that this is somewhat contradictory because the dimension of this part here, and this one, this dimension of x is just j, and then the dimension of, let's consider it to be y is j minus 1 because we have assumed that V1, the V's are what? Are basis elements. Okay. That means that uh, this means that T is not injective. This is if we restrict, if it's not injective, uh, restricted 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 to uh, the dimension of the span of V1 to V sub j. This means there exists a vector V, which is T of V is equal to 0, and for some V not equal to 0. Okay, so that means that this one, which is greater than this, some of these vectors here are 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 0, regardless that V sub j is not 0. Yeah, it's not injective. So because it's not injective, this is a contradiction. This means that, okay, restricted to the, so here, this means that P is not injective. If it's not injective, automatically we get a contradiction. A contradiction to the uh the invertibility assumption. Okay, this is a contradiction, and hence our assumption is hence V sub I is equal to 0 for all j. This is a contradiction to our assumption. What's the assumption? The assumption is V sub j is 0. There exists a V sub j not equal to 0. So in this means that, right, not V, but lambda sub j equal to 0. This means that lambda sub j is not 0 for all j from 1 to our here n. So I think this ends the proof. And because of this theorem, we can easily prove some statements like the following statement on the determination of eigenvalues of an upper triangular matrix. Suppose again we get an operator in the vector space B with upper triangular matrix with respect to some basis, and then the eigenvalues of our T are precisely the diagonal, not the diagonal, but the entries on the diagonal of the upper triangular matrix of our T. So to prove this is just an easy consequence of the previous statement. So let us consider a matrix M of T, B lambda 1, and then up to lambda n, here all 0, be the desired matrix of our T, then what? Let's take lambda be a scalar. Then we look at the matrix of T minus lambda I. We just applying this one via our polynomial. This is lambda 1 minus lambda. And then we get some asterisks here, which are non-zero. And then all here we have lambda minus lambda, lambda n minus lambda, and here below is 0. But here, does your lambda, T minus lambda I is not invertible if and only if lambda is equal to 1 of lambda sub 1 up to lambda sub n. Therefore, the statement is thus your lambda is an eigenvalue of our linear operator T if and only if lambda is one of the numbers in the diagonal given by lambda 1 up to lambda n. So basically, what it says is the diagonal entries are the eigen values for our operator. So now let's consider a linear operator on F3 as an example given by the following equation. So this is the example earlier, 5y plus 3z, and then 8z. Then the matrix with respect to the standard basis is given by 2, 1, 0, 0, 5, 3, and then 0, 0, 8. In this case, this is upper triangular. That means the eigen values are 2, 5, and 8 is by previous theorem. Okay, that's it for our example. Now, let me call this the end of our recording for today. For the next video, we will just go over the definition of an eigenspace, the space of eigenvalues, eigenvectors, I mean, with respect to some lambda. And then we will also consider the relationship between diagonal matrix, or specifically we will consider diagonalizability. Diagonalizability of our matrix. That is, we can write the matrix as a diagonal matrix. The matrix of the operator as a diagonal matrix. So here, yeah. And then that's it for the next meeting. So maybe I'll stop the recording here.